4 colligative. We have done all 4 colligative properties, and from there we have found that colligative property is directly proportional to the amount of substance taken and inversely proportional to molecular mass of the solute. Okay, so colligative properties are directly proportional to the amount of solute and is inversely proportional to their molecular masses. Okay, now see here. Let us go for the first one. Relative lowering in vapor pressure. What did you find here? Delta P by PA0 is equal to WB MA WA MB. See, the whole thing is the relative lowering of vapor pressure. It's directly proportional to the weight of the substance, inversely proportional to the molecular. Second, elevation in boiling point. Delta TB is equal to KB into WB 1000 MB into what? W. See here. This is directly proportional to the amount of the substance, inversely proportional to the molecular mass. Okay. Now, depression in freezing point. AF WB 1000 divided by MB. Second, see here. This is directly proportional. Inverse. And osmotic pressure. I is equal to what? WB R into T and divided by so this is for your information. I did not write it, but I know you have all forgotten. You have think that it is a ritual, like this religious ritual. We come and sit down quietly, but we don't hear what priest says. So it is you also thought that by Tuesday, Thursday, and Saturday you have to attend a mass. So now we have found all these 4 colligative properties can be used for determination of molecular mass. Okay. All these 4 colligative properties are useful for determination of molecular mass of solid. Okay, let me fill up ink. You can go for this one. One, depression in sorry, not depression. Relative lowering in vapor pressure, because we are going to find na, so we will do here method. So what is the molecular mass? Mb is equal to Wb Ma delta P by Ph0 into that. So by this method we can find. Then this is your summary. Elevation in boiling point method. In this case, what do you do? Let n now Mb into Kb into Wb into 1000 divided by delta Eb into W. Third, depression in freezing point method. It is same only. Mb Kf Wb 1000 delta Tf into W. And the last one is osmotic pressure method. What we do here? Mb is equal to Wb R into T divided by pi. Right. See now. So all this method can be used for the determination of molecular masses of the solute. But out of this four methods, we find that osmotic pressure method is the best one. So let me write down its advantages. So just to tell this one, I have to spend around 15 minutes, otherwise because you have forgotten everything. Now, what are the problem with others? When I go for relative lowering in vapor pressure, when I set up the instrument, if little bit leakage is there, then the vapor will escape. If the vapor escapes, the pressure will decrease. And the substances are colorless. They may not have a smell also. Then how to detect your instrument is leaking? Even a fine small hole also through which the vapor can go out. So in that case, if you calculate the molecular mass of the substance, it will be wrong. Now, if you go for depression in elevation in boiling point and depression in freezing point, sometimes we find the difference between the boiling point of pure solvent and boiling point of the solution. The difference in the temperature comes in the second decimal place. See, the normal thermometer which you use in our laboratory or at home for measuring our body temperature, you can read up to first decimal. Suppose your body temperature has become 97.4. But if you want to read the second decimal, then the thermometer has to be long, because so that you can divide it. Okay, these days, of course, we can use thermocouple. With the help of thermocouple, you can find out the difference in forms of digital. Otherwise, in the normal laboratory, whatever laboratory that we have in our country or maybe in other places, it is difficult for us to read the difference in the second or third decimal place. So if you cannot read it correctly, then there will be error. And if the delta TB is wrong, then molecular mass also will be wrong. So these are the many things we can say in theory. In theory, everything nice, looks nice. But when you put into practice in the laboratory, then you come across that different experimental problems are there. Technical problems are there. Okay. But when you go to osmotic pressure, we find the method is found to be more and more advantageous. Why? Because osmotic pressure method we carry out at room temperature. You don't have to heat, you don't have to cool it. And even at the room temperature, the osmotic pressure that you calculate, it is a large quantity. And when the quantity is large, then there is chances of error is very less, because it doesn't come in decimals. So in that case, the probability of error is less. And as the probability of error is less, in that case, you can find out the molecular more appropriately. Second, osmotic pressure, even for a dilute solution, is also not negligible. Why I'm saying? Because when we can measure, we can find out the molecular mass of those substances whose solubility is very, very less. Then whose solubility is very less? These are the big molecules. We call it macromolecules. Okay, or polymer. Big size. So even for a dilute solution also, that osmotic pressure is a pretty good quantity. Moreover, it is found to be extremely advantageous or helpful when you try to calculate the molecular mass of biomolecules. Biomolecule means those molecular substances which remain in an ambient condition in our body or in plants. That is, you don't have to heat it and you don't have to cool, freeze it. So whatever the condition in which they remain in the living system, same condition can be created in the laboratory without heating. And even if the solubility is less also, no problem, we can make a very dilute solution. All right. So we can measure the molecular masses of those biomolecules to a perfect way because it does not undergo decompose. Otherwise, in normal circumstances, the biomolecules will disintegrate or decompose. So these are the, and the last one which I want to tell you, the colligative property, that properties that we have calculated, we have made always a molal solution, MOLAL, molal solution. In relative lowering in vapor pressure, we make a molal solution. In depression in freezing point, we make a molal solution because we see the constant itself is called molar elevation constant, molar depression constant. But in osmotic pressure, we make a molar solution. This is the basic difference. This may be asked in your entrance exam. What is the basic difference that uh, osmotic pressure and others? In osmotic pressure, we use a molar solution, and in other three, we use a molar solution. Okay, so let me write here. Advantage of using osmotic pressure method over other colligative property methods for determination of molecular masses. What will write now here? Its value is large for every dilute solution, and it can be measured. Second, it can be measured as it is extremely advantageous for determination of molecular masses for biomolecules. It is because the solutions because the measurement is done at room temperature, by which biomolecules do not undergo any decomposition. Moreover, sparingly soluble polymers, sorry, moreover, polymers with low solubility molecular masses of polymers with low solubility can also be determined. Yes, the osmotic pressure for a very dilute solution is also found to be pretty simply. So the chances of is all the polymers molecular mass will be determined by this method. So as the value is more, chances of error is less, and it can be measured at room temperature. Okay, and We use largely for determination of molecular mass of biomolecules because we carry out their experiment room temperature, so they do not break down, decompose. And the substances whose very poor solubility also, their molecular mass also can be determined. Okay. So now we'll write note. Molar solutions are used instead of molar solutions. Okay. See, osmosis is a common phenomenon in living systems, whether it is a plant kingdom or animal kingdom. Okay. So in plant and animal kingdom, you have seen that sometimes the fluid from outside the cell it goes inside the cell, and sometimes the fluid inside the cell it goes outside the cell. Okay. So in this case, in biological system, what you call them? We call them as plasmolysis. In biological system, osmosis is being regarded or mentioned as plasmolysis. And if the fluid from outside goes inside the cell, we call them as endosmosis. And from the fluid from inside the cell, if it goes outside the cell, we call them as exmos, uh, uh, exosmosis. Okay, so we exosmosis and endosmosis. All right. So this you know much better than me. I am um, studied biology maybe 40, 45 years back. That too also up to class 12. So I have totally forgotten. All right. Now, if you have made two solutions of two different substances, and if their osmotic pressure is found to be same, then we call them as isotonic solutions. Okay. If the osmotic pressure of two different solutions made from different substances, then it is called is, iso, isotonic or isosmotic Please remember, osmotic pressure is a colligative property and it depends upon the number of the particles present. If the two solutions of different substances are isotonic, then please remember they have the same number of molecules presented. So isotonic or isosmotic solutions are equimolar in nature. That is, they have same number of solute moles. Okay, these are different substances, but number of molecules are same. Okay. This is a very important thing. All right. Now, if they're different, then what should we say? Hypertonic. If the osmotic pressure of a solution is more than the osmotic pressure of another solution, then it is called hypertonic.
Done, sir.
Okay. Now, if it is less than, what should we tell it? We call it hypotonic. So
Done, sir.
okay. Now see here. This is very important. See, within the cell we have fluid, na? So it has a osmotic pressure. We find that if you make a solution of sodium chloride, 0.91%, okay, mass by volume, has the same osmotic pressure of the fluid that you have within the red blood cells. So we say it is isotonic with the RBC fluid. Okay. Now, so this is the RBC. All right, RBC, and it is found to be osmotic pressure found to be isotonic with 0.91% sodium chloride, or you call it saline water. All of you now are acquainted with saline water, because if the patient goes to hospitals, then for immediately we have given drip. Na? So this drip is nothing but saline water. Why do you call it drip? Because it falls drop by drop. Now, if this cell, the fluid is inside, if this RBC is kept in a sodium chloride solution, okay, whose concentration is more than 0.9 mass by volume percent, then what is going to happen? Here it is concentrated, so the fluid from inside will come out, because this is the process of osmosis. So what will happen gradually? It will shrink. It will shrink. So all the water from the cell will come out. The person will suffer from dehydration, and it may lead to his death. Okay. So now what is this? What do you find? As you know, osmotic any colligative property depends upon the amount of the substance present. Here sodium chloride is more, so the osmotic pressure will be more. So this is a hypertonic solution. Similarly, if you keep this RBC in a sodium chloride solution, 0.91%, 0.91%, if it is, we find that this is, sorry, in this case, what you find here, the solution is less than that. Then what will happen? Osmotic pressure here, pressure is less, here will move. So the fluid from inside will go. When the fluid from inside will go, what will happen? It will swell, and time will come, it will burst. So the RBC will swell and ultimately it will burst. So in that case also, one patient will die. So one has to be extremely careful. In industry, when they make saline water, they have to be very, very careful. Many a time it happens that we blame doctor, but doctor is not making the solutions. It is from the spurious company who are selling it, who might be that the bottle may be cheaper by 10 to 15%, and we go think that no, that is better. What will happen? Just to save maybe 100 or 200 rupees, your patient huh, comes into coma and he died. All right. So this has to be carefully read. So I'm tired of writing. How much you should write here? Is 0.91% mass by volume. Solution of sodium chloride, known as saline water, is isotonic with fluids inside the RBC cells. Now, if a sodium chloride solution is solution having concentration more than 0.91% weight by volume comes in contact. Means when it will come in contact. If it is injected, if it is injected to human body. Okay. Then the fluid from RBC will come out due to osmosis. And the, and the RBC cells will shrink. On the other hand, if a sodium chloride solution having lesser concentration than 0.91% weight by volume comes in contact with RBC cells. Then fluid from outside will move inside the cells by osmosis. Osmosis leading to swelling of cells or URS. Okay, now you are growing up. Many a time you have to be accompanied to hospital with any patient. You should know. Osmosis we are observing or doing almost every day in our life. Osmosis occurs. See, when your body becomes very dry, why do you go and take bath? Some amount of the fluid goes inside and make us fresh. Okay. See, osmosis is also being done for preservation of food. You will find the food which you want to keep store it. In that case, to that we use either a lot of, because food gets spoiled because of microorganisms. All right. Either you put lot of salt or you put lot of sugar. Take the example of pickles. We put lot of salt there. Or if you go for, say, jelly, jam, and all this thing, you put lot of sugar there. And in case of the pickles, you put lot of salt. Because all these microorganisms, when they settle on these foods, as because too extremely concentrated amount of the sugar or the salt is there, so the body fluid from those microorganisms, they come out by exosmosis, and by that way the microorganisms die. If you go to vegetable market, you will find during summer time to time they sprinkle water, otherwise vegetable looks stale. Maybe that he has got it 2 hours back, then also it will look stale and nobody is going to buy the stale vegetables. What will happen? He will sprinkle water. So again, by osmosis, the water will go inside the vegetable and it will look fresh. If you keep carrot in your house for 2 days, you'll find it wilts. You don't feel like eating. But if you keep this carrot in water for 2-3 hours, again it will look fresh. Why does it happen? Because of osmosis. Okay. Now we go for reverse osmosis. reverse osmosis. Acha. In some of your house, are you using AquaGuard for filtration in your house? AquaGuard. Anyone is using AquaGuard? I don't know about others. Those who are having own houses, they might use. I also don't know how many of you have your own houses. Tell who is using AquaGuard in your house? Hmm? Hello, Gitanjali.
Yes, sir.
Are you using AquaGuard in your house?
Yes, sir.
Do you know what is the technique used there?
I don't know, sir.
Very good. You are only supposed to drink water. Why should you know about this? Huh? Okay, very good. See, we have found we have kept two solutions. Okay, this is this one. Say it is pure solvent, means water, and this is, say it is saline water. So now you know, due to osmosis, what will happen? The fluid will move. Huh? This is semi-permeable membrane. So the water will move. So gradually, what will happen? You will find this layer will go down and this layer will go up. So to stop this movement of solvent molecules, what we do? We apply pressure on this. Okay, we apply pressure. These are piston pressure. When the pressure becomes equal to the osmotic pressure, then the movement of the solvent molecule stops. In that case, you find in both the arms, both the arms, the level is same. Now, if you apply more pressure, if P is more than pi, this is osmotic pressure. In that case, we find the water from the solvent from the solution side will move towards the pure solvent. So this is called reverse osmosis. If pressure more than osmotic pressure is applied on the solution side, right, then the solvent from solution moves toward the pure solvent side through semi-permeable membrane. This phenomenon is called reverse osmosis. It is used for desalination of seawater.
Done, sir.
See, those in the coastal area, say take the example of Middle East. They have everything. Okay, plenty of money, huh? But they don't have drinking water. Desert. And there hardly one or two rivers are there. Rainfall is very, very less. In that case, then in that case, what they'll do? Will they drink petrol? No, because it's being, you'll find on the one side they are having sea, but sea water also they cannot drink. So in that case, they take the help of the reverse osmosis and they convert the sea water for drinking. But very interesting thing, you know, same technique is being used in your house, in your aqua guard or quick filtration system. They also go for reverse osmosis. But please remember, in advanced countries these days, people do not drink RO water. This aquaguard water they don't drink. You know why? Because when you go for reverse osmosis, only the solvent molecule comes. Minerals are missing. All right. But minerals are essential for us. In our body, we require different types of minerals, especially the metals. So these are all free from minerals. So drinking RO water is same as that of drinking of distilled water. This is the problem. So RO water is not good for our health. All right. So now, today if I take around 45 minutes more, I think I'll be able to finish this chapter. But I'll not do because it will be too much strenuous for you. So today I'll finish it here and Thursday I'll finish this chapter. And please go through all this thing that I have taught you because I have sent you note also. After finishing, if you have anything which you could not understand or you have some doubt, ask me. Then last Thursday I'll discuss. And from Saturday, I'll start a new chapter. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Okay. Then, well.
Thank you, sir.
Ah.
Thank you, sir.